Okay, we're stuck now with lesson 4, and today's lesson is about Bayes' rule and a little bit more in depth and some more examples in Bayes' rule. There'll be two videos. One will talk through again examples of Bayes' rule, and then more details, and then we'll look at the next part of the lesson at just exclusively examples and go through those quickly. So you'll remember lesson 1 or 2, we talked about Bayes' rule, that we started out with some information and prior probabilities about our sample space, about events A and events B, and the intersection of events A and B. So we have prior probabilities, and then we know something about this random experiment. We get information, and we'll know, and for this example, that B occurs. And when we know B occurs, that reduces our sample space down to just this event B. And event B consists of all of those events plus including those that are in the intersection with event A. And so once we know this, then we can apply Bayes' theorem and compute posterior probabilities. In this case, what's the probability of A given B? And we know that's this intersection. It's the ratio of this intersection area to the whole area, which is exactly what this divisor is. It's the intersection probability of A and B divided by the probability of B, which represents if you can see this, it represents this represents that area, and of course the probability of B represents all of B inclusive. So that's where that ratio derives from. Okay, so next I want you to notice something, that by applying this definition, we know that the probability of A and B, which is this intersection, by applying Bayes' rule, it's the probability of A given B times the probability of B, plus if we just reverse those and apply the definition, it's the probability of B given A times the probability of A. And so by applying, we're going to see how we can apply this application of this definition in some examples that are coming up. So let's look at an example next. And this is kind of relevant to what's going on in today's world with with COVID. And let's suppose that we have this situation where 1 in 1,000 people is affected with a disease for which we have a test. And what we know is that in the cases when the person has a disease, we will get a positive result 99% of the time. But when the person does not have the disease, the test still shows a positive result 2% of the time. So if a person were to walk, if you're the doctor or the tester and the person walks in the door who you don't know anything about, and that person has a positive test, then what's the likelihood or what's the probability that the individual actually does have the disease? And so to begin this process, we're going to have to define some terms, define some random variables as we're talking about. So let's start out by, we're going to say that the letter D, and actually rather than trying to write, let me type this out. We're going to let the letter D is going to be the event that a person has the disease. And we're going to let the letters ND the fact that the person be the event that a person does not have the disease. And again, you can choose any letters that you wish, but it's just ND is no disease, and D, of course, means the person does have the disease. And then we're going to also define another set of random variables where we're going to say P is the test as a positive result, and then we're going to have neg is going to stand for the event is that the test has a negative result. And actually, it's not P. It's going to be. Let me redefine that. It's not going to be P. It's going to be pause. So it'll be consistent. Pause is the test is as a positive. So those are our four different outcomes. So you just have to ignore. Let's ignore this one. All right. So the pause, neg, D, and ND are our definitions. Now, what else do we know? Well, we know in advance, we know that the probability of D is 1 in 1,000, or in terms of decimals, it's 0.001. And because of that, we know that the probability that a person who walks in the door without the disease is 0.999. And the reason that we know this is that since there's 1 in 1,000, if there's 1,000 people that could walk through the door, only one of them would have the disease, and the other 999 would not. We also know the following. Now, this is going to be a little tricky, but we also know a conditional probability. We know the probability that the test will be positive given the person has a disease is, so for those people that have the disease, given that the person has the disease, the chance that the test is positive is 0.99. We also know the probability that for a person who does not have the disease, the chance that there's a positive test given the person does not have the disease is 2%. It's only 2. And that comes from, of course, that comes from our information, where this is returns the result given, and you can read this, when the person has the disease is the same as saying given that the person has the disease, the positive result is 99% of the time. And then similarly, given a person does not have the disease, the test is positive 2% of the time. Now, so you should ask yourself now, well, what if the person doesn't have the disease? What's the chance that the result will be positive? And so this again will be probably difficult to think about, but think about this carefully. The probability that the person has a negative test given that they have the disease is 0.01. There's a 1% chance that you'll get a false negative. In other words, you get a negative even when the person does have the disease. And there's the case where there's the probability that there's a negative test result given that the person does not have the disease. And see, this is what you want to have happen. This is 0.98. It's the complement of these two are complementary, and these two are complementary. And that's based on the condition of the information that's given. All right. So now we're gonna ask ourselves, well, how are we going to use this to answer the question? Because what do we want to calculate? And let me change colors here, because if the test, it says if the test is given randomly to an individual and given that the test is positive, what is the chance that the individual has the disease? So what we really want to calculate here is that we want to calculate the probability that the person has the disease given we have a positive test. That's what we don't know. But we can use Bayes' rule to get that. And I want you to notice again, this is very different from this. They're not the same thing. We're going to calculate this value, the answer to the question, using Bayes' rule. And we're also going to introduce a tool that's called a probability tree to help us organize this information and come to the answer. Let's go to the next slide. But here's the where we're going to introduce a probability tree to help us analyze the situation. And what we have is we're starting out, we have two possible things could happen. You could almost consider that this is a patient, and this is my patient over here, who's walking in the door. And there's two things that this patient could be. That person could either have the disease or not have the disease. Those are the only two possible outcomes. So there's two branches to this tree. They either have the disease or they don't have the disease. And so we know that we can then assign the probabilities, because as we've already seen, there's a 1 in 1,000 chance that the person has the disease. There's a 99.9% that this person does not have the disease. So we assign the probabilities to those branches of the trees. And these probabilities are called, as is shown here, these are our prior probabilities. This is the information that we know in advance, or we know prior to anything else. And so then let's about what happens next, and let's just consider this branch where the folks have the disease. What's the next thing that will happen to these people? Well, what will happen is there's going to be a random event that's going to happen. There's an event that happens. We're going to give the test, and that test, there's two possible outcomes. The test will either be, as you might think, the test is either going to be positive or the test is going to be negative. Okay, And so, and then that's the same thing, because we're going to give a similar test to the people that don't have the disease, but there's only 2 possible outcomes that can occur. So we've got 4 different branches to this tree. All right, and again, I'm going to abbreviate this, but well, no, I won't. This is positive and negative. Those are the only 2 things that can happen. Okay. And then, as we've done before, we're going to assign the probabilities associated with. So this is the probability that are associated with this. The probability that there's a positive result if the person has a disease, 0.99, and we had already talked about all of these probabilities that that are associated, we did previously. And these probabilities are called conditional probabilities, right? And so that's just by definition. And now all we're going to do is we're going to use this tree, and we're going to multiply the branches of the tree together to calculate the respective, what's called our joint probabilities. And so we're going to calculate this branch, the 0.001 with the 0.99 to calculate a value at the end of this branch. We're going to calculate 0.001 times 0.01 to calculate a value associated with this branch, and so forth through the tree. And we're going to see that on the next slide. So here's our values, and here's our calculation. And these values at the end of our probability tree are called joint probabilities. So this is the probability that a person has the disease, and which is the intersection, and gets a positive test, probability that they have the disease and there's a negative test, probability that there's no disease and a positive test, probabilities no disease and a negative test. Now what I want you to try to see next is in how many situations does a positive test occur? Well, there's 2 cases where a positive test occurs. And those 2 situations are here and here. So there's 2 ways that a positive test can occur. And so consequently, if we had thousands of people doing this over and over again, the total chance that a positive test could occur is going to be the sum of these 2 values. And then that's going to be add these together, that's going to give us the probability that a test given to anyone who comes through the door, this is the chance that that's going to be positive. Because now this is going to get us part of the way there. And you'll see if you add those 2 together, this is going to be 0.02097. That's the chance that there's a positive test. So now the question is, we're ready to apply Bayes' rule, and we've got all of the information that we need. And what do we need? Well, because what do we want to calculate? We want to calculate the probability that the person has the disease given that there's a positive test. That's the important thing. That's the information that we want to know. And by using Bayes' rule, as you'll remember, if we apply the definition, this is the probability that the person has the disease and is positive, has a positive test. And that's going to be divided by the probability that there is a positive test. Okay, now, can you see where all of this information comes from? Well, the numerator, this value is the numerator. And hopefully you can see this value. I'm not going either too fast or too slow. This value becomes the denominator in what we want to calculate. So our final calculation is 0.00099 divided by 0.02097. And when we do that calculation, you'll find out this is 0.047. So the answer to our question is there's only, even if there's a positive test, there's only about just about a 5% chance that that the person has the disease, and so that may not be particularly helpful. But let's go ahead and because we would like that to be, and there's a couple of ways to resolve that. But let's go ahead and look at a different example with slightly different information. So the same situation, but now we're going to suppose that the incident rate is 1 in 25 rather than 1 in 1,000. And so what that means is the probability that the person has the disease is 1 in 25, rather than 1 in 1,000, which is 0.04. And so that means, of course, the probability that the person does not have the disease is 1 minus that, or 0.96. Right? And that's the only thing that's changed. Now we're going to use, again, the probability tree, and this is going to look very much the same. And we're going to substitute in here the probability we have the disease is 0.04. The probability that person doesn't have the disease is 0.96, right? And we want to do our same multiplications through the table. And to do that, see if I can get when we multiply 0.4 times 0.99, the value that we're going to get is 0.03396. You follow through, and 0.04 times 0.01, the value that we're going to get there is 0.004. three zeros. And then the value that we are going to get when we multiply 0.96 times 0.02 is 0.0192. And finally, when we multiply 0.96 times 0.98, we're going to get 0.9408. Hopefully you can check through that to verify that that's accurate. Now, one of the things I want to do is the following, and this is to kind of make you understand this relationship, because what we've done on this left side of this probability tree, we've calculated these probabilities. So these are the prior probabilities times the conditional probabilities are going to give us the joint probabilities. And so, and then this on the far side is just a mirror image of this probability tree. But on this side, we're going to calculate marginal probabilities, and we're going to instead of do this multiplication, but this multiplication is still going to do yield our joint probabilities. All right, so now let's figure out, and we're going to work this tree from the outside in. So the first thing that we want to calculate, like we did before, is what's the probability that a test will be positive. As we said before, there's two situations when this, excuse me, when this occurs. And that's this situation where there's a positive result here, and that's this situation when there's a positive result there. And notice these arrows. This is going to be associated with this part of this probability tree, and this part is going to be associated with this part of our probability tree. And so in order to get the probability that we have a positive result, we're going to add 0.396 and 0.0192 together to get that probability that it's a positive test, just like we did in the previous case. And in this case, sorry, I'm trying to get my cursor in the right place. In this case, that probability when you add those two values together is 0.0588. And so we can get this probability that the test is negative in one of two ways. Number one, we could add together this value and this value, because as before, this is the case where we get a negative, the two cases where we get a negative result. And again, that's associated a negative result that's associated with this part of our decision tree. And so when we add those together, the probability that the test is negative, you can get this one of two ways. It's going to be 1 minus the probability that there's a positive test, since only two outcomes, or when we add those two values together, we're going to find out that it's 0.9412 when we add those two values together. So now here's what, using Bayes' rule, see if I can help make this connection. Using Bayes' rule, this is our marginal probability. And instead of A, this is the positive. So that's this value here. And what we want to do, what we want to calculate is this value. And we know by Bayes' rule, this value times this value has to equal to this value. And so now, in order to calculate this missing value here, how do we calculate that missing value? Well, of course, hopefully you can see the relationship. This is going to be, you would have to do the division, 0.0396 divided by 0.05, it's a 588. And when we do that calculation, we're going to see that this value is 0.673. So interestingly, after making just one change, the probability that the test is positive, or the person has the disease, the positive test is 67% compared to 4%, 5% previously. And the answer to the other question, where we wanted to determine, which is also important, to determine the probability, the chances of a false negative test, or in other words, the chance that the person has the disease given there's a negative result. And hopefully you would see, let me get a different color, that's going to be, in other words, that's this value times this value by Bayes' rule. Multiplying those together is going to give this value. And so in order to calculate this, this is going to be 0.0004 divided by 0.9412. And when you do that to division, this comes out to be 0.0004. Also, it's hardly changed. We get a different color actually. .0004, or 4/100ths of 1%, 0.04%. So if there's a negative test, it's very, very unlikely that you have the disease, given that there's a negative test, which is a good, this is a, as you would expect, this is a good result. And this seems to be a good result too. Right? So that's how we use and manipulate Bayes' rule to answer various questions with respect to information and results of the test. The next part of this lesson will be using Bayes' rule in different examples, and I'll go a little bit more quickly. Hopefully that makes sense. If not, let me know if you have questions.